Welcome to today's lecture on software faults, and we'll explore real-world disasters caused by software failures and uncover critical lessons for building reliable systems. So we'll learn about understanding the impact of software faults, analyze some famous case studies, and learn some prevention strategies. So by the end of this lecture, you will grasp how minor software errors can lead to massive failures and why rigorous testing is important to prevent them. So first of all, we need to know what are software faults. A defect in code that causes unexpected behavior. This can be in terms of logic in the program logic, which can be erroneous. It can be because of some race conditions or buffer overflows. Software faults are often hidden flaws in code. For example, even a single misspelled character can bring down entire systems. So now we move to some examples which were very costly software faults. First one is the Ariane 5 explosion, which was a rocket sent to outer space, and it crashed on its maiden flight due to a reused module from Ariane 4, which required it to do a 64-bit floating point conversion to a 16-bit integer for the Ariane 4 module. This caused an overflow condition. As a consequence, the rocket crashed and resulted in a 370 million loss in total. So the lesson learned was that we must test the reused code if we want to reuse it in newer context or in some other setting. Another example of a costly failure is the masked climate orbiter. This was again due to a conversion error. In this case, it was from metric to imperial conversion. So one team used the metric units and the other team used the imperial units, and once they had to communicate between the module developed by these two teams, there was not a proper conversion. As a consequence, the spacecraft burned in the Mars atmosphere and never reached the surface. So the lesson learned was we need to clearly specify the interspace specification between different modules. One more example of a costly failure was of the Therac-25 radiation machine, which was used to treat cancer patients by exposing them to radiation. But in this case, its software skipped some safety checks, which need to check when an operator types too fast. So this case was not checked. As a consequence, patients were exposed to radiation which were much more than the desired ones. It resulted in the death of several patients and several others were injured. Consequently, the analysis was done and it was found out that it was again due to a software fault, which didn't detect the typing some of the user who were too fast for the machine. Another example of a costly failure is the Toyota unintended acceleration, which was caused in 2009 and 2010. It was caused by a software glitch used in these cars, which resulted in the cars to accelerate uncontrollably. And as a consequence, there were 89 deaths and 1.2 billion dollars were paid in settlements by Toyota company to the those who were affected by these sort of acceleration and brakes. So the lesson learned was that we even need to even focus on the edge cases, even for some simple embedded code as was used in this case. Another example of a costly failure is the Pentium FDIV Bug 1994. And it was due to a flawed division algorithm in the CPU, and it costed the Intel company 475 million loss. And the lesson learned was that we need to validate hardware and software interactions properly. Otherwise, again, we can have very costly failures like this one. Yet another example of a costly failure is the Knigh Capital, which occurred in 2012. So the fault was because of an unremoved test code in the trading algorithm. This costed the company $460 million in just 45 minutes. And the lesson learned was that we need to resort to version control and deployment checks before deploying the software in its environment. So Knigh Capital used the untested code which triggered a financial collapse. So we must audit the code before deployment properly. So common themes of all these faults that sometimes the code was reused without testing, error handling was not done properly, edge cases were ignored, and how we can overcome these is to deploy some of the prevention strategies, like we can perform code reviews, or we can make use of pair programming where a couple of people sit, one of them is an expert programmer and then the other one is not that expert, and he guides the less expert person to write better code. We can make use of automated testing by means of tools which can focus on unit and integration and testing. We can use formal methods for development of safety critical systems, as were some of the examples we just discussed were safety critical systems like that of Ariane or the Mars orbiter. We also need to focus on fail-safe design, which should consider graceful degradation in case of a error condition is encountered by the program. So we can prevent failures with layered defenses, and we need to test early and we need to test often, and we should never assume that code is flawless. So we can make use of the following references for the purpose of these examples which were discussed in this video, and more interested users can look into these references for a deeper insight. Thank you for joining, and let's aim to build software that doesn't crash or kill. And if you liked this video, please do consider subscribing, commenting, sharing, and giving it a thumbs up. Thank you.